All right, share the screen and we come back here. All right, let's take a look at this. You know, the angle is the popular section that you generally could use for the small truss, the truss in the factory and so and so. Even though the pipe or the tube become more popular, but many times you'll find the angles. And many times you may find yourself, having to recalculate the strength of the angle to may strengthen the old structural system and so and so, okay? So I used to draw something about this before, but let me begin again from the beginning, okay? So let's say when you have the angle, well, it looks like that. Now let me underline one thing right away, that in our country, only equal leg angles, you know what angle is like that, are available. So at least you don't have the unequal leg, you don't have the unsymmetric one. It's good for you. Now, for the angle, generally this X and Y axes are not the principal axis. So I have mentioned before that the principal axis will contain the maximum and therefore the minimum value. So if XY is not principal axis, it means that the minimum moment of inertia is not on this axis. We don't want to know the maximum, we would want to know the minimum because that's a weak point, okay? The principal axis is somewhere in this Z, okay? So that means in the old days, when they designed the angle, they would have to consider the radius of gyration of the green axis. This is the principal axis. Axes. So that means they contain R max and R minimum. So if you go and look at the properties of the angle from the tables provided by TIS and so, they generally have like, they would give you Rx, Ry, and then I believe they call that Ru and Rv. So because most of the time the angles are used for the diagonal webs and so, so you know the unbraced length is the length of the member itself. So you could just easily consider the minimum radius of gyration to get the maximum slenderness ratio, right? And it's always lie within this Ru and Rv. So you look at the four values and generally you would find the minimum, the smallest one from one of the Rus or Rvs, I don't remember. And in the old days, they would just use that R minimum to design the angle, and they just calculate the K over R based on the R minimum. But there is another problem with the angle. You see, the centroid of the angle is there. It's not even on the member itself. And generally the centroid does represent where the load actually is. And it is true. At least, even though not physically, but theoretically, the load is acting through this red point. That is so true. So that means one thing, because we cannot put the load through the air, right? We need to transfer the load onto the member by the physical means. So your angle will have to carry the load from the support by itself, which means that it will create the problem that we call eccentricity. Eccentricity means that your load doesn't act on the centroid, so it creates an extra force due to the fact that your load do not coincide like this. And eccentricity will create extra moment of torsion depending on where you look, okay? So the current method will take care of the fact that we have this problem. The old method would just use, you know, the minimum KL over R and then get on with the business. But the new one, we need to further modify KL over R to account for the fact that there is this eccentricity problem with the angle. Okay, now let me try to write you this, okay? Because let's say you have F critical, excuse me, okay? Let's say you have F critical and you have two formulas to calculate it. It's like 0.658 Fy over Fe, then multiply by Fy when, you know, KL over R is, that's my R, excuse me. When KL over R is less than 4.71 square root. And then you have 0.877 Fe when KL over R is greater than 4.71, okay? And square root. And then your Fe is equal to pi square E over KL over R squared. So once you have the KL over R, you calculate Fe and you just plug Fe into one of these formulas. That's how we do it with the compression member, right? But it's pretty much the same with the angle. The procedure for the new one is the same, except that before you do this, this KL over R must be modified. And once you modify it, you calculate Fe, you check the KL over the new KL over R and pick the right formula. And the rest is the same. But for angle, that's my angle, okay? KL over R must be modified before the usual calculation. Okay, so how we modify it? Let's go back and take a look from this. Okay, so they have the Rx. Rx, generally that is the X in the direction of buckling. So that becomes, it depends on where you have the gusset, but it becomes either your typical X or Y direction now. So because we have equal leg angle in this country, so it doesn't matter whether or not it's Rx or Ry, they are the same. You can, you know, put it this way to save you some more pain. So we don't use R minimum in the modification. You just pick Rx or Ry, calculate this. If it's less than 80, modify your K over R with this formula. When it's greater than 80, modify with that formula. Okay, and this set is, yeah. It's done like that. So I take this out of the specification and summarize for you. For equal leg angle of the planar truss, that this is truss in 2D, we have this modification depending on the ratio of KL over R of L over Rx. And when you consider space truss, that's a 3D truss. The space truss is like the one in the canopy in front of your KFC. That's a space truss. you use this set of formula, and that's all. I can tell you that I'm not gonna put you through this in the exam or in the project. This is just for your knowledge alone. Okay? So is there any question? Hello? There any question about the angle? And of course, the angle, you should always check the local buckling. And the limit of the angle is less than the flange, because it's the leg is the unstiffened element, the same, but it's not as strong as the flange. Okay. So question. Okay, there is no question. So I'm gonna count to 3 and then I'll stop the share and I will stop the record. Okay. 1, 2, 3. Stop the share and stop the record.